Lab 2, Motion of a Falling Object. The purpose of this lab is to track a falling object's motion by dropping the ball straight down. To explain this, we will use Newton's second law, specifically the momentum principle, where force equals the mass times acceleration, which can be rearranged to be F net divided by mass equals the change in velocity divided by the change in time. That is derived from the velocity and position update formula. The overall setup for this lab was to find the motion of a falling object using Tracker and Python to determine what forces were acting on the fallen object. Specifically, I was trying to determine the weight force, which is negative m times g, and the negative y direction, and another force acting on the object due to air resistance, which is the drag force. First, for this lab, I observed the motion of a falling basketball from rest straight down, which was initially slow, then sped up. I used Tracker's calibration stick to calibrate my height, which is 1.753 meters, and started tracking the ball at frame 35, which was the last time the ball started its downward motion, and I stopped at frame 51 when the ball hit the ground before it bounced back up. I set the initial time at 0 seconds, and the initial position was negative 1.97 e to the negative 2 in the negative y direction, which was marked by point mass to plot the object's position at each time step. Next, I used Python to create a computer model of the weight force only, and the weight force and the drag force. Using the information gathered from Tracker, I was able to change the code for both models to obtain a computer model for these forces. For the weight force only, I changed the code for the ball's mass, initial conditions, and velocity stay the same, which were 0. Added the gravity constant of little g equals 9.8 meters divided by second squared. Changed the net force acting on the object. In this model, it was Fg equals negative mg times j hat. For the gravitational force, I calculated W, which is negative ball's mass times g times j hat. Since the object is falling near the Earth's surface, the gravitational acceleration is 9.8, and j hat will be in the negative y direction. Since the only force acting on the object is gravity, F net will equal the weight force, since F net is the sum of all the forces acting on the object. For the drag force and weight force model, we are assuming that there are two forces acting on the object, the drag force from the air resistance and the weight force. The drag force can be defined as the magnitude of velocity times b times j hat, where b is the proportionality constant, which depends on airflow and the property of the object. I found b by trial and error and matched my final position of my computational model from the gravity force only and observed force to determine my b value. Next, the code was changed to reflect that Fd equals negative b times velocity and the F net equals grav force plus drag force in order to calculate the new net force, and that accounts for the drag force and gravitational force. Unlike gravity, the drag force acts in the opposite direction because drag force goes in the opposite direction of velocity. I combined the data from Tracker and my two computational models from Python to create a graph where the blue dotted line is observed data from Tracker, the red line was from the Python data of gravitational force only, and the yellow thin line was for gravitational and drag force. The first few seconds of the graph, you can see all three lines are on a similar path, but as time progresses, the observed line does not match with the drag and gravitational force in the gravitational force only line. The initial velocity was set as 0, so drag force could not work opposite of velocity, thus all three lines are similar in the beginning. However, as time progresses, they begin to diverge, leading to a computational model overestimating how far the ball fell, as the graph shows the object fell further than it actually did, which could be due to the drag force. The drag force, the gravitational force, for both models lie on top of each other, showing the forces acting on the basketball were similar. Thus, in both models, they were the only forces acting on the ball. The discrepancy of the observed data from Tracker could be due to human error when setting the time frames and selecting the point mass in the center of the ball. In addition, the middle part of the graph, there is a separation from the gravitational and drag force, which could be due to the door in the back of the video distorting the camera, as well as a better b constant could have been selected to fix the observed data. Finally, another model may need to be conducted to show how the drag and gravitational force could have overpredicted the observed data because the magnitude of drag is proportional to the square of speed. Discussion question 1. Only the model with drag and gravitational force could reach terminal velocity because the net force would have to equal 0. The gravitational force only model could not reach terminal velocity because there's no other force acting on the gravitational force because there's no air resistance acting on the object to make the net force 0. As time continues and gravitational and drag force graph continues, there will be a point where the drag and gravitational force will have the same magnitude of force and cancel to make the net force equal to 0. Discussion question 2. Since the ball is being thrown The ball will have a greater velocity than at rest, so the drag force will be greater initially at first. Since drag force is present working against gravity, the terminal velocity will reach faster than if the ball was dropped from rest, because seen in the drag force and gravitational force graph, the drag force will not be slow at rest, so it will already work against velocity to reach the terminal velocity sooner.